All right. Have you ever stopped and thought about how something as simple as lighting a candle,
Yeah.
it's basically, harnessing a chemical reaction that we've been trying to control for millennia?
It's one of those things, right?
We're diving into the world of combustion today,
Yeah.
and we're way beyond the basics with this textbook chapter you sent over.
Yeah, it's funny you should say that because we see fire almost every day,
Yeah.
but how often do we actually think about the science behind it? What's going
Yeah.
on behind that flickering flame?
Exactly. So to kick things off, let's define our subject here.
Okay.
The textbook defines combustion as a chemical reaction where a substance reacts with oxygen to release heat and light.
Right.
But what does that really mean?
Yeah.
I mean, I'm picturing that experiment we probably all did in school,
Right.
burning magnesium ribbon.
Yes, the blindingly bright light.
Yes.
That's combustion in action. The magnesium reacts with the oxygen in the air, creates that intense light and heat. And it's not just fancy science experiments. This is happening all around us.
Yeah.
That charcoal grilling up your favorite burger.
Yeah.
Combustion.
Oh, wow.
The process that gives you the energy to take a bite of that burger.
Yeah.
Combustion.
Okay, that's kind of blowing my mind.
Right.
So my lunchtime sandwich is basically just undergoing controlled combustion.
Well, yeah, I mean,
I'm guessing our bodies are a tad more complex than a Bunsen burner, though.
oh, yeah, you're right. The human body is incredibly complex, but at its core, when we break down food, it reacts with the oxygen we breathe,
Yeah.
and that releases energy as heat. It's how we keep going.
Okay. Yeah.
But let's talk about igniting that fire, so to speak, because the textbook mentions ignition temperature.
Yes.
And that feels like a pretty key concept here.
It's like the magic number.
Yeah.
A substance needs to hit before it'll actually catch fire.
Right.
But what makes that temperature different for, say, a piece of wood versus kerosene the text talks about?
It all comes down to their molecular structure.
Okay.
Think of it like this. Some substances are like a house of cards, loosely put together, easy to knock down.
Right.
Those have weaker bonds, break apart easily, and boom, they react with oxygen at a lower temperature.
Okay.
Others are more like fortresses,
Yeah.
tightly bound, needing a lot more heat, a higher ignition temperature to get them going.
Right.
Kerosene is like that house of cards igniting easily,
Makes sense.
while wood is more of a fortress,
Yeah.
needing that extra kick.
Okay. That makes a lot more sense. So knowing this isn't just about passing science class,
Right.
it's crucial for things like preventing fires, right?
Absolutely.
I mean, if someone doesn't realize how different those ignition temperatures can be, that could lead to disaster.
Oh, yeah.
Especially with something like spontaneous combustion, which sounds absolutely terrifying.
It is terrifying, and unfortunately not as rare as you might think. The textbook uses the example of phosphorus, which is fascinating and terrifying.
Yeah.
White phosphorus has such a low ignition temperature that it can literally ignite in the air on its own.
What?
No match needed.
Wow.
That's why those old school matches were phased out.
Yeah.
Way too risky.
Right.
It's the same principle with things like coal dust explosions in mines or even hay fires.
Oh, right. That's why we can't have nice things, I guess.
Right.
But seriously, if something can ignite that easily, how do we even stand a chance at putting out fires?
Yeah.
It can't just be throwing enough water at the problem, surely.
You're right. Water isn't always the answer.
Okay.
Remember the fire triangle?
Yeah.
Fuel, air, and heat. You need all three for combustion.
Right.
Removing even one stops the fire in its tracks, and that's how we fight back.
Okay.
Water is great at cooling things down, bringing the temperature below that crucial ignition point, essentially hitting the brakes on the whole combustion process.
So it's like dousing a campfire.
Exactly.
You're not really removing the fuel source. The wood's still there.
Right.
But you're making it too cold to keep burning. That's why they use those massive water cannons on building fires.
Exactly. But let's say you have a grease fire in your kitchen.
Right.
Dumping water on that is a recipe for disaster.
Oh, yeah.
Water's denser than oil.
Mm.
It'll just sink and potentially spread the burning oil even further.
Right.
Or imagine an electrical fire.
Yeah.
Water and electricity are a dangerous mix.
Don't mix.
That's where CO2 extinguishers come in.
Yeah.
They're like the specialist firefighters of the extinguisher world.
CO2, like what we breathe out.
Yeah.
How does that work to put out a fire?
It's denser than air, acting like a heavy blanket to smother the flames, displacing the oxygen, fueling the fire. Plus, no risk of electrocution. It's all about choosing the right tool for the job, and that comes down to understanding the science behind those flames. But this whole time we've been talking about fire in a general sense.
Right.
Did you know there are actually different types of combustion?
Oh.
I mean, it's not a one-size-fits-all situation.
Different types of combustion. I'll admit, I kind of assumed fire was fire. But the more we talk about this,
Right.
the more I realize there's a whole world of complexity I never even considered.
It's like anything else. The more you zoom in, the more you realize how much there is to learn.
Right.
The textbook mentions a few different types.
Okay.
Let's start with rapid combustion, because that feels like the most familiar one.
Okay, rapid combustion. Is that what we see with something like a gas stove? You turn the knob, spark it up, and boom.
Exacting controlled flame.
You got it. That's rapid combustion in action.
Yeah.
The gas mixes with oxygen, and with that little spark of ignition, you have a fast, intense, but controlled burn.
Okay.
It's the same principle behind those Bunsen burners we talked about earlier, just on a slightly less exciting scale.
Right. So if rapid combustion is your everyday cooking fire, what about something like spontaneous combustion? That still feels like the stuff of scary stories, even though we touched on it earlier.
Yeah, it sounds dramatic,
Yeah.
but it's very real.
And it highlights why understanding things like ignition temperature and those underlying chemical structures is so important.
Right.
Remember how we talked about white phosphorus igniting on its own?
Yeah.
It all comes down to how easily a substance can react with oxygen and generate enough heat to reach that critical ignition point, sometimes without any outside help.
Okay, that makes sense. But it's not just random chemicals that can spontaneously combust, right? The textbook mentioned things like coal dust and hay as well.
Right.
How do those just decide to burst into flames?
They don't just decide, thankfully,
Okay, good.
but their structure and properties make them more susceptible. Take hay, for example.
Okay.
It's essentially dried grass full of air spaces.
Right.
If it gets damp, bacteria can start breaking it down, generating heat. Because hay is a good insulator, that heat gets trapped.
Yeah.
The temperature rises, and if it hits that critical ignition point,
Yeah.
boom, spontaneous hay fire.
Wow. So even something as seemingly innocent as a haystack can become a fire hazard under the right or wrong, I guess, conditions. Okay, I'm adding beware of damp hay to my mental list of fire safety tips right alongside avoid piles of white phosphorus. What about explosions, though? Those feel like combustion on a whole other level.
They're definitely the rock stars of the combustion world.
Yeah.
Think of fireworks, those brilliant bursts of light and color.
Right.
They're essentially incredibly fast, intense combustion reactions. You're packing a lot of energy into a small space, and when it ignites, it releases that energy almost instantaneously, creating a rapid expansion of volume and explosion.
So basically explosions are like combustion hitting the fast forward button.
Exactly.
No wonder fireworks are so loud and impressive.
And those vibrant colors.
Yeah.
Those come from specific chemical compounds included in the fireworks. It's a fascinating blend of art and science.
It really is. This whole deep dive is making me look at fire in a whole new light.
Oh.
We've gone from burning magnesium ribbon to spontaneous combustion to exploding fireworks. It's amazing. Let's switch gears for a second and talk about flames themselves. I mean, they're kind of the poster child for combustion, wouldn't you say?
Absolutely. Flames are the visible evidence of those chemical reactions we've been discussing.
Right.
They're like the heartbeat of the combustion process.
Okay.
And just like a heartbeat, they have a structure, a rhythm that dictates how they behave.
Wait, really? A flame has structure? I always just assumed it was wildfire.
It might seem that way,
Okay.
but there's a fascinating level of organization within a flame. The textbook uses the example of a candle flame,
Right.
which is a great way to visualize this. Picture a candle flame in your mind.
Got it.
Okay, now focus on the different zones you see.
Okay.
There's that dark inner cone right around the wick. Then it transitions to a brighter yellow as you move outward, and finally a faint, almost invisible outer layer. Each of those zones represents a different stage of the combustion process.
Oh, right. I remember learning about this in school, but I'll admit it's been a while.
Yeah.
So that dark inner zone, that's where the wax is vaporizing, but not yet fully burning, right?
Precisely. It's like the warm-up act before the main event.
Right.
The wax melts, vaporizes, but it's only when those vapors mix with oxygen in the air that the real party begins.
Okay.
That brings us to the middle zone, the luminous zone, the brightest part of the flame.
Okay.
That's where combustion is in full swing.
And that's the zone that gives off the most heat, right? Since that's where the real burning is happening.
It seems intuitive,
Yeah.
but it's actually the outermost zone, that almost invisible layer, that's the hottest.
Really?
It's subtle, but it's where combustion is most complete. Those tiny unburnt carbon particles from the middle zone finally find enough oxygen to burn, fully releasing their maximum energy as heat.
So the outer zone is like the grand finale where the temperature peaks.
Exactly.
That's why the textbook talks about goldsmiths using the very tip of the flame for melting.
Exactly.
Yeah.
They're harnessing that peak temperature zone for precision work.
Yeah.
It just goes to show, even within something as seemingly simple as a candle flame, there's this incredible interplay of chemistry and physics happening.
This is blowing my mind. But speaking of real-world applications, we've talked a lot about how things burn, but what makes a good fuel? It's not like we can just go around burning anything we find and expect good results.
You're hitting on a crucial point. Not all fuels are created equal, just like you wouldn't use a wrench to hammer in a nail.
Right.
Different fuels have characteristics that make them better suited for specific tasks.
So what should we be looking for? What separates a so-so fuel from an excellent one?
The textbook lays out some key factors.
Okay.
Availability is a big one. We need fuels that are readily available, not buried in some remote, inaccessible location.
Right.
Cost effectiveness is another. A good fuel should be economically viable to produce, transport, and utilize.
Right. Doesn't matter how efficient a fuel is if it costs a fortune to get your hands on it.
Yeah.
What else?
Ease of use. Ideally, you want a fuel that's easy to ignite burns at a manageable rate and doesn't require complex extraction or refining processes.
Right.
And of course, energy output is crucial. We want fuels with a high calorific value.
Calorific value, that rings a bell. It's essentially how much energy a fuel releases when it burns, right?
Exactly. It's a measure of the energy content, typically expressed in kilojoules per kilogram.
Okay.
A fuel with a higher calorific value packs more punch, so to speak, releasing more energy per unit burned.
Okay, that makes sense. But it's not just about how much energy a fuel can produce, right? We also have to consider the byproducts of combustion. Burning some fuels can release harmful pollutants into the environment, and that's a whole other can of worms.
You're right, and it's a crucial consideration, especially as we talk about the environmental impact of combustion. As the textbook pointed out, no fuel is perfect.
Yeah.
It's always about balancing the benefits with the drawbacks.
Which brings us to the million-dollar question. What's, the environmental impact of all this burning we're doing?
I have a feeling this is where things get a bit heavy. It's kind of like ironic when you think about it. Combustion has been like essential for human progress, giving us everything from cooked food to the ability to power our homes and vehicles.
Right. But it's also impacting our planet, in some pretty significant ways.
Yeah. It's a classic case of trade-offs, unfortunately. The energy released through combustion has revolutionized our world.
Yeah.
But those benefits have come at a cost. One of those immediate impacts is air pollution.
Right, like those unburnt carbon particles the textbook talked about, the ones that create sooty smoke and cause respiratory problems?
Yeah, when fuels don't burn completely, they release these tiny particles of carbon, along with other nasty byproducts into the air we breathe.
Right.
These particles can travel deep into our lungs, leading to respiratory illnesses, aggravating asthma, and even impacting heart health.
And it's not just those visible signs of pollution, right? What about carbon monoxide? The textbook called it the silent killer, which is honestly a bit chilling.
It's a serious concern, and because it's colorless, odorless, and tasteless, you wouldn't even know you were being poisoned. It's a tragic reminder that we can't always see or smell danger.
Right.
Carbon monoxide prevents our blood from carrying oxygen effectively, and prolonged exposure can be fatal.
That's why it's so important to have carbon monoxide detectors in our homes, especially with things like fireplaces or gas appliances.
Absolutely.
But even if we move past those immediate health concerns, there's the whole issue of greenhouse gases and climate change.
Absolutely. Carbon dioxide, a major byproduct of combustion, is a greenhouse gas. It traps heat in the atmosphere, contributing to the gradual warming of our planet, which we're already seeing the effects of today.
Yeah, melting glaciers, rising sea levels, extreme weather events. It's a pretty sobering list. And it's not just carbon dioxide we need to be concerned about, right?
You're right. The textbook also mentions sulfur dioxide and nitrogen oxides, which are released when we burn fossil fuels like coal and diesel.
Right.
These pollutants react with water and oxygen in the atmosphere to create sulfuric acid and nitric acid.
Wait, acid in the atmosphere. What happens to that?
It falls back to Earth as acid rain. Imagine watering your garden with lemon juice. That's essentially what acid rain does to ecosystems. It damages forests, acidifies lakes and streams, harms wildlife, and even corrodes buildings and infrastructure.
So we're talking about a chain reaction of negative consequences. It's clear that we can't just ignore the impact of combustion on the environment, especially as our energy demands continue to grow. But the textbook did mention cleaner fuel options like CNG. Is that a sign that we're moving in the right direction?
I'd say it's a step in the right direction.
Okay.
CNG, or compressed natural gas, burns much cleaner than gasoline or diesel, producing fewer harmful emissions. And there's a lot of research and development happening in the realm of renewable energy sources like solar, wind, and hydropower, which hold great promise for a more sustainable future.
It feels like we're at a crossroads. We need energy to power our world, but we also need a livable planet. It seems like the choices we make today about the fuels we use and how we manage those combustion processes will have consequences for generations to come.
You've hit the nail on the head. It's a complex issue with no easy solutions. But understanding the science behind combustion, both its benefits and its drawbacks, is the first step toward making informed decisions about our energy future.
Speaking of informed decisions, it's time for us to spark a little further thought with our final provocation. And this one's for you listening. We've uncovered how combustion works, the different forms it takes, and the impact it has on our world. But now that you're seeing the world through this combustion lens, what other everyday phenomena might involve this chemical reaction in ways we rarely stop to consider? Keep that fire for knowledge burning, and we'll catch you on our next deep dive.